We have discussed the principles of uniform and non-uniform acceleration before. In this discussion, we shall limit ourselves to the field of uniform acceleration, one where the acceleration has one value for the duration of study. We do this because the aspect of motion that we are most interested in is motion under the influence of gravity. We can make the situations more complicated later, because if we learn how to handle uniform acceleration, non-uniform acceleration just requires a slight adjustment in our approach to the maths. Uniform acceleration generates straight line graphs of motion. Changes in velocity are uniform, so velocity time graphs have nice straight lines. We know how to work out displacement and acceleration from these graphs through geometry from our previous discussion, so it should become easy to derive some more complicated equations of motion using these principles. First, let us establish some terms. In our discussion, we were talking about properties from average and instantaneous motion. For average motion, we have two sets of distinct variables, those at the beginning and those at the end. For the purposes of our discussion, it is useful to differentiate between velocity at the beginning of motion and a velocity at the end of the motion we are discussing. Velocity at the beginning is called initial velocity. It is given the symbol u. The velocity may change over the course of our calculation, so we need to give the final velocity a label. This label shall be v and is called final velocity. The average acceleration of an object is given as change in velocity divided by change in time. Change in velocity is the final velocity minus the initial velocity, so our first equation of motion is a equals v minus u divided by delta t. For the purposes of this discussion, we shall call change in time simply time, so the equation becomes v minus u over t. The value of acceleration does not change as this is uniform acceleration, so we can rearrange this equation with impunity. Final velocity v equals initial velocity plus acceleration times by change in time. Looking at the situation this way, it becomes obvious. The final velocity is the velocity you started with, plus however long you're accelerating for times the value of that acceleration. Let's say you started off at 10 meters per second, and you accelerated at 2 meters per second, every second, for 10 seconds. That means that every second your velocity increased by 2 meters per second. After 1 second, it was 12 meters per second. After 2, it was 14 meters per second. Until after 10 seconds, it was 10 plus 2 times 10, 30 meters per second. From the initial velocity, the acceleration, and the time, you can work out the final velocity. On a graph, you can see this equation as a little triangle on a velocity time graph. The gradient of the hypotenuse of this triangle is the acceleration. The width of the triangle is the change in time, and the start and end points of this line are the initial and final velocities. The displacement an object has whilst changing velocities is worked out using the idea of average velocity divided by time it took to change velocities. As we have constant acceleration, we can use a general form of average, as the velocity will change smoothly. The average velocity of an object is the sum of its velocities divided by the number of velocities included. We only have two velocities, the initial and final, and so our equation is initial velocity plus final velocity divided by 2 multiplied by the time it took to change. S equals u plus v over 2, all times by t. This can be represented as a parallelogram on a velocity time graph, with sides u and v and a width t. We can work out the area of this parallelogram from the average of the sides times the width. This gives us 2 of our eventual 4 equations we'll need to describe all aspects of motion with uniform acceleration. Both of these equations can be derived from geometries of a velocity time graph. The first is the acceleration as derived by the gradient of a triangle, sides v minus u and t. The second equation comes from the area of a parallelogram, sides u, v and t. From these two equations we can derive two more equations and thus produce equations that have four of the five properties of uniform acceleration motion, namely displacement s, initial velocity u, final velocity v, acceleration e and time taken t. This is why these equations are called SUVAT and shall be summarised in the next discussion.